All right, hello everybody. This is Mr. Fasoni. I'm continuing on with the Chapter 6 problem example sessions in YouTube here. So this is going to be Chapter 6.3, which is all about logarithms and logarithmic functions. So we already talked through this entire lecture. We did some examples, but I want to do a few more. I've got them here on the right. I guess I should just do this. So our first example type was converting from logarithmic into exponential form. These are from the book. I'm just going to kind of just speed through these. So let's get started. So if you'll remember from the lecture, our logarithms are written as log base some base b, whatever that base is, of y will be equal to x. Remember, a logarithm is just basically an operation that asks a question. It says, what power of b will give me y? So it's asking for the power for the exponent if it's attached to b to the x equals y, which means we've got an equivalent exponential statement. We can say b to the x power equals y. Man. All right. So these are equivalent statements, or maybe related statements. Maybe not equivalent is the best thing to say, but these functions are inverses of each other. The exponential functions and the logarithmic functions are kind of like opposites, like plus and minus, or multiplication and division. So because of this, we can very quickly write through and figure out our answers here. I'm just going to go through and circle all my bases on this really fast. On the first one, I've got log base 3, then log base 6, log base 1/2, log base 4, log base 7, log base 3. And then my y values are all the things that are right next to the base: 9, 1, 16, 4, 343, and 1/3. And then finally, my x values are the things on the other side of the equation. All right, so all I'm doing is, rearranging things, really. So I'm going to write these. I'm not going to switch colors on these. I'm going to use this purple color on all of it. But for the first one, log base 3 of 9 equals 2. It's basically saying what power of 3 will give me 9? Well, we know that 3 to the second power will give me 9. So that's a conversion there. We're rewriting the equation in exponential form from logarithmic form. So for this next one down, what power of 6 will give me 1? Well, we know anything to the power of 0 will give you 1, with the exception of 0 itself. So 6 to the 0 equals 1. Next one after this is what power of 1/2 will give me 16. So this goes into our negative exponents. And if we wanted to just translate this straight over, it's going to be 1/2 to the negative 4th power equals 16. I'm going to come back to that one after we do these next three. Number 6 here up the upper right, what power of 4 will give me 4? Well, anything to the first power will give me itself. So 4 to the first power gives me 4, which is what we have there. 4 to the first power gives me 4. What power of 7 gives me 343? Well, that's going to be 7 to the third power. And then finally, what power of 3 gives me 1/3? Well, that's going to be 3 to the negative 1 power equals 1/3. Just a quick note on these negative exponents. Remember, anything to the negative 1 power is just another way of talking about the reciprocal. So x to the negative 1 is the same as 1 over x to the first, or just, we don't need that first power, 1 over x. And that works for any negative power. If I've got x to the negative 3/5 power, I could rewrite it as 1 over x to the 3/5 power. Okay, so if I'm thinking about 1/2, powers of 1/2, and I'm trying to get to 16, so 1/2 to the question mark equals 16. Well, I can turn that 1/2 into a 2 to the negative first power, to the question mark power. And then I happen to know that 2 to the fourth power equals 16 already. So what I can do is I can just rewrite this as 2 to the negative first to the fourth is equal to 16, or 2 to the negative, oh, not to the negative fourth. What am I doing here? Oh, yes, 2 to the, well, 2 to the negative 1 to the fourth is 16. Sorry, I goofed up there. To convert this back, though, I want to convert this back. 2 to the negative 1 is another way of saying 1/2, right? So 1/2 to the negative fourth power equals 16. That's kind of a clunky explanation. What I'm saying basically is that 1/2 and 2 to the negative first power are the same thing. And we know that 2 to the fourth is 16. So 1/2 to the negative fourth is the same as 2 to the fourth, which is also going to be 16. All right. Let's go over to this one really quick. Log base 3 of 1/3 is equal to 1. Well, we found that that was 3 to the negative first equals 1/3. Well, we just talked about reciprocals. 3 to the negative 1/1 is the same thing as 1/3, and 1/3 definitely equals 1/3. That's for number 10. All right. So next up, let's go to the other direction, rewriting the equation in logarithmic form from exponential form. So again, we have exponential form, which is b to the x equals y. And that's equivalent to log base b of y equals x. So I'm just converting from exponential form to logarithmic form. Again, I can just go through, find all my bases, 6, 16, 125, 12, 5, and 49. I can find all my powers, second power, negative first power, 2/3 power, 0 power, negative 1/2 power, and 1/2 power. And then finally my y values, 36, 1/16, 25, 1, 1/25, and 7. So if I'm going to convert this, it goes very fast again. And I'm going to keep this all in one color again because it's just too much to change back and forth. But it's going to be log my base b, which in this case is 6. So log base 6 of 36. So what power of 6 will give me 36? Well, that's going to be 6 to the second power, or 2. And I can continue along with this. Log base 16 of 1/16. Well, we already know the reciprocal of a number, just a whole number, will give me 1 over that whole number. So my power would be negative 1. Log base 125 of the number 25 will equal 2/3. We'll talk about that in a second. And then over on the right side here, 12 to the 0 power, that's going to be log base 12 of 1. So 12 to what power equals 1? Well, that's going to be 0. 5 to the negative 2 is equal to 1/25. That's just going to be log base 5 of 1/25 equals negative 2. And then finally, log base 49 of 7 equals 1/2. Or in other words, 49 to the 1/2 power equals 7. So just a quick note on these fractional powers. This is also a review from Algebra 1. So a fractional power, so if I've got x to the 1/2 power, for instance, all that's asking for is the square root of x. And how that works, use some color coding here. This 1, you can consider a 1 either on the variable, or you can consider it outside if you want as well. And the 2 is technically my index for my square root. Remember that square roots all have an index. If there's no index listed, then it's assumed to be a 2, which is a square root. I wish we didn't teach math that way. I wish we started by putting the index in there, because most of the time when there's not a number listed, we're assuming it's either going to be a 1 or a 0. The square root kind of messes with that assumption. But the index here is 2, and that's basically saying what value times itself, so a value to the second power, is going to equal the value on the inside. If I extend this, I can really put any values in there, right? If I have, let's say, x to the 5/3 power, well, that's just going to be it's going to be a root, but the 5 is going to be the power of the inside, and the 3 will be the index on the outside. So this is saying the third root of x to the 5th power. So what number times itself 3 times, or what number to the third power will give me x to the 5th? And depending on what your numbers are, you might get some kind of crazy decimal there. But that's basically how the notation works. So if I'm thinking about number 15, that's saying, well, basically 125 to the 2/3 power. That's effectively saying 125 squared. What is the third root of that? So what number to the third power will equal 125 squared? Well, you can set up an equation here. This is a little bit weird to think through, but basically x to the third power is 125 squared. Well, maybe 125 doesn't ring a bell, maybe it does. Hopefully it rings enough of a bell to go, I think that's a power of 5, which that is 5 to the third power. So on the right side of the equation, I've got 5 to the third power squared. On the left side of the equation, I've got x to the third power. If I solve this through, 5 to the third power squared is yet another way of saying 5 to the 3 times 2 power, using our power rule. And then I can just continue from there. That means that x to the third is equal to 5 to the 6th power. Okay. Well, we're almost done. Some number times itself 3 times, or some number to the third power, x times x times x, is equal to 5 to the 6th. Well, if you think about 5 to the 6th power is 5 times 5 times 5 times 5 times 5 times 5. I know I'm doing this very visually, but maybe this will help. Well, if you think about that, we can kind of just match things up. X, 5 times 5. X, another 5 times 5. X, another 5 times 5. So x is really equal to 5 squared, or 25, which is what we had in this example here. There's my 25 right there. Similarly, number 16 is actually easier. It's just saying 49 to the 1/2 power is equal to 7. Well, if you just think about the left side of the equation, 49 to the 1/2 power is just 49 to the first, and then taking the square root of that, or the second root of that. Well, the square root of 49 is 7. We're not worrying about plus or minus, because we're not necessarily solving for x. We're just evaluating. When we evaluate the square root function, we just think about the positive values unless otherwise instructed. All right, so let's continue. These ones I think we had to evaluate. Yeah, evaluating logarithmic expressions. So in these ones, I don't have my y value, or I don't have my x value, I mean. I've got log base b of y, but I don't have the x's. So I'm just solving these. That's what we did in the lecture. That's what we'll do here really quick. So log base 7 of 49, that's just saying 7 to the x equals 49. Well, that means that x is equal to 2. Next one, log base 1/2 of 1. That's just saying 1/2 to the something power is equal to 1. Well, we know anything to the 0 power will be equal to 1, so that's going to be 0. Next one is saying 8 to the x power equals 1 over 512. Well, that's another strange one, but I can very quickly talk about that. I'll just go below it and I'll write the next one. I'll do the number 24. I'll just do that to the left. Okay, so 8 to the x power is equal to 1 over 512. Okay, well, 512 might ring a bell to you. 512 is just 8 to the 3rd power. So if 8 to the x is equal to 1 over 512, then that means that it's going to be a power of 1 over 8. So that means I'm going to rewrite this. 1 over 8 to the negative 1 power is going to equal 1 over 8 to the 1st. And I want to get to 1 over 512. Well, I know that 8 to the 3rd power is 512. 8 times 8 times 8, there's 512. That means I can rewrite this. I can say 1/8 to the 3rd power is equal to 1 over 512. If it's 1/8 to the 3rd, then really, because I think I messed up earlier, 8 to the negative 1st is equal to 1 over 8. If I'm trying to figure this in powers of 8, I can rewrite this 1/8 as 8 to the negative 1st. So 8 to the negative 1st to the 3rd is the same as saying 8 to the negative 3rd power, and that's going to be equal to 1 over 512. Another way you can think about it is you can take 8 to the 3rd power. That's going to equal 512. Well, the reciprocal of that is just going to be 1 over 8 to the 3rd. And I can then rewrite that. If I want to write it in powers of 8, I can just take this 8 to the 3rd out of the denominator. And that gives me 8 to the negative 1/3 power, or 8 to the negative 3rd power. All right. Similarly, number 24 says log base 10 of 0.001. So it's saying 10 to the x power equals 0.001. Well, hopefully you just see that these are powers of 10 here. 10 to the 1st is 10. To 10 to the 2nd is 100, and so on. We just keep on adding zeros as we multiply. So if I go in the other direction, I talk about negative powers. 10 to the negative 1st is going to be 0.1. Negative 2nd is going to be 0.01. And then 10 to the negative 3rd is going to be 0.001 for 1,000th. 10 to the 3rd is 1,000. 10 to the negative 3rd is 1,000th. So I'm going to get a negative 3rd power, or not 1/3, negative 3rd power on both of these. If I could write. So both of these are to the negative 3rd power, and I can actually check the 10 one really easily. 10 to the negative 3rd power, you type the 3 first and then hit this little plus minus sign. If I hit equal, hey, look, 0.001. Same thing with 8. 8 to the negative 3rd power. It's going to give me a nasty looking decimal, but if I take the reciprocal of that, which is just this 1 over x key, sure enough, there's that 512. So the reciprocal of 512, which would be 1 over 512, is 8 to the negative 3rd power. All right, let's continue along. Then we moved on to evaluating things with calculators. This is very, very fast. So remember, on our scientific calculators, whether you own one or you have it on your phone or you're using the computer-based one, they all have these nice keys, the common log and the natural log. So if I want to calculate these, I can very quickly do it. Natural log of 12, type in 12, hit the natural log key. It's 2.4849. I'm going to round that up to 2.485. Change my color. Let's go blue. That one's done. Continuing forward, the common log of 2/7. So what I got to do is I got to do 2 divided by 7 to get this repeating decimal. From there, I'm going to hit the log button. And it gives me my common log of 2/7 is going to be negative 0.544. And I don't need to do any rounding there. So negative 0.544. And then this last one is an expression that has a couple things in there. We've got log of 0.6, and then we're adding 1 to it. Don't let that freak you out. Just do the log of 0.6 first, and then add 1 to it. I get 0.778. And again, no rounding needed. And there we go. I don't like the location that I put those. Let's do this again. All right. So evaluating with a calculator is very straightforward. The last bit we have here is using the inverse properties of logarithms and exponents. So basically, if I take the log of an exponent with the same base, log base b of b to the x, for instance, then all this stuff cancels and I'm left with just the x. If I do it the other way around, if I take b to the log base b power of x, again, I get a bunch of stuff that cancels and I'm left with just the x. So this just takes a little bit of getting used to, but it's not too bad. So we'll go through these ones kind of quick as well. This is my b, 7. There's my b again. So this is b to the log base b of x. Cancel, cancel. It's going to leave me with x. Again, 3 to the log base 3 of 5x. Well, all this stuff cancels. All I'm left with is the 5x at the end. E to the natural log of 4. Let's do some rewriting. This is equivalent to e to the log base e, because the natural log is base e of 4. Well, now I can cancel, right? I know they're the same base. You don't have to rewrite it, but just to illustrate what's going on. 38 is very similar as well. 10 to the log of 15. That's a common log. If there's no number listed, well, that's just saying the same thing as 10 to the log base 10 of the number 15. These all cancel and I get 15 at the end. All right. These last two are not going to be too bad. This is going the other direction. I'm starting with the logarithm and I've got an exponent inside the logarithm. So this is log base 3 of 3 to the 2x power. Same idea holds again. Log base 3 and the base of 3 go away and I'm left with 2x. And then finally, this last one's a little bit funny, but don't let it freak you out. But the natural log of e to the x plus 1. Well, this is just the equivalent. I'm going to zoom in here so I have some space to write. This is the equivalent of writing log base e of e to the x plus 1 power. I'm going to put this in parentheses. Well, now I can see what cancels. These cancel and these cancel, which results in my final answer just being x plus 1. Again, not too bad. Just understanding that structure that we went over in the lecture notes, and from there we can cancel things out. So if I'm starting with an exponent, I can use it, put it inside of a logarithm to get rid of the exponent, or get rid of everything but the exponent value, I guess I should say. Or if I'm starting with a log, I can put that log in the exponent for some base that matches my base for my logarithm, and everything will cancel out except for that y value that was in the original logarithm. All right. I think that's it. Do I have any others? No. So that is it. We burnt through those questions pretty fast. I'll go ahead and upload this on the channel. The homework will be out sometime today as well. It's about 2 p.m. on Wednesday, so I should have it out sometime this afternoon or evening. And that homework will be due next Monday as well, along with the 6.2 homework. All right. As always, let me know if you have questions. Otherwise, I will see you in class.